Underwater tunnels should be straight up impossible, but engineers found a terrifyingly smart way to make them anyway. Because think about what they're actually doing. They're connecting two pieces of tunnel deep under the sea, under mud, under rock, under crushing water pressure where humans were never meant to work. And sometimes the digging teams are on opposite sides of the ocean, like one country's crew starting from one end, while the other country's crew starts from the opposite side. They can't see each other, they don't have normal GPS underground, and they don't get a second chance if they miss by even an inch. A tiny slip-up and the walls won't line up, the floor won't match, the seals will fail, and water starts leaking into a structure that's supposed to be bone dry forever. So the real question is, how the hell do engineers make two tunnel sections meet perfectly when the whole connection point is buried under the ocean and they're basically blind? And before engineers connect anything, they have to map the entire route underwater. Survey boats move across the surface, sonar scans the seabed, drilling rigs pull up long core samples, underwater cameras check the terrain, and engineers study every layer below the water. They need to know where solid rock begins, where soft mud sits, where cracks could let water in, where the seabed suddenly drops, and which route gives the tunnel the best chance of staying dry and stable. For a bored tunnel, the large drill machine has to stay inside the safest layer underground. Engineers aimed the route through a layer called chalk marl. It had fewer cracks and allowed less water through than the layers above it. So before engineers connect two tunnels underwater, they first have to find the one underground layer that won't fight them the whole way. And once they find that layer, then they send in the machine. A tunnel boring machine, or TBM, which is way more than a giant drill. It's basically a moving underground factory. At the very front, a huge circular cutter head spins against the rock or soil. Metal cutting discs break the ground apart. Openings in the cutter head pull that broken material into the machine. Then, conveyor belts or slurry pipes carry it back through the tunnel and out to the surface. But the whole machine also has to move forward. So powerful hydraulic cylinders push against the tunnel lining behind it and drive the cutter head deeper into the ground. Then, just behind the front shield, another system lifts curved concrete segments into place. Crews bolt those pieces together into a complete ring, one ring after another. That lining supports the tunnel and keeps the ground from collapsing behind the machine. The Channel Tunnel used 11 TBMs to dig its 3 parallel tunnels from the British and French sides. But underwater, pressure creates another serious problem. The soil, rock, and seawater ahead of the machine constantly push toward the open tunnel face. If that pressure wins, the ground can collapse and water can rush inside. So in softer ground, engineers use an earth pressure balance TBM. The machine keeps pressurized soil inside a chamber behind the cutter head. That pressure matches the force coming from outside. Too little pressure and the face can cave in. Too much and the machine can disturb or lift the ground above. So while the TBM digs forward, it's constantly balancing the seabed in front of it. And there's also another way to do it. Instead of digging the tunnel underground, engineers build giant sections on land. Then they take those sections out to sea and sink them. This is called the immersed tube method. The Fehmarn Belt tunnel between Denmark and Germany uses this approach. First, dredging ships cut a huge trench into the seabed. For this project, that trench stretches around 40 to 50 meters wide and roughly 12 to 15 meters deep. Crews have to remove about 20 million cubic meters of seabed material. That's enough soil to fill thousands of Olympic-sized swimming pools. Meanwhile, inside a massive factory onshore, workers build the tunnel itself as 79 giant concrete segments. Each standard segment measures around 217 meters long, about 40 meters wide, and 10 meters high. Inside each one, engineers build 2 road tubes, 2 railway tubes, and a smaller service passage running between them. Once a segment finishes curing, crews install temporary steel walls across both ends. Those walls seal the segment and turn the giant concrete box into something that can actually float. Tugboats then pull it out of the factory basin and guide it toward the construction site. When it reaches the correct point above the trench, cables and positioning systems hold it in place. Crews start filling ballast tanks with water. The segment gets heavier. It slowly drops beneath the surface. Then, cranes and guidance towers lower the entire structure toward the seabed, centimeter by centimeter. Now, engineers have to line up this 73,000-ton concrete box with the section already sitting in the trench. Because sinking it is difficult, but connecting it without letting the ocean inside is the part where the real engineering starts. Each tunnel segment has a huge rubber gasket fitted around one end. When crews lower the new segment into the trench, they stop it just a short distance from the segment already in place. Then, powerful cables and hydraulic systems pull the two segments together. As the gap closes, the rubber gasket starts to compress. That creates the first watertight seal. But at this point, water still sits between the two temporary steel bulkheads inside the tunnel ends. So crews pump that trapped water out. And as the pressure inside the joint drops, the water pressure outside pushes the new segment even harder against the old one. Basically, the ocean squeezes the joint shut. Once engineers confirm that the seal holds, crews enter from inside the dry tunnel. They cut away the temporary bulkheads, then they connect the floors, walls, cables, drainage pipes, ventilation ducts, and emergency systems across the joint. Now, those two giant concrete boxes act like one continuous tunnel, and crews repeat that process again and again, section by section. Once the full tunnel sits in place, dredging ships cover it with sand, gravel, and protective rock. That extra layer shields the structure from currents, erosion, dropped anchors, and ships passing above. So engineers don't simply lower a tunnel into the sea. They align it, seal it, pump the joint dry, use water pressure to lock it together, connect every system inside, then bury the whole thing beneath the seabed. But even after that, the tunnel still isn't finished, because an underwater tunnel is usually a whole network. Take the Channel Tunnel. It actually has 3 parallel tunnels under the English Channel. 2 large rail tunnels carry trains in opposite directions, and a smaller service tunnel runs between them. Each rail tunnel measures about 7.6 meters wide. The service tunnel measures around 4.8 meters wide. And every 375 meters, short cross passages connect the service tunnel to both rail tunnels. So if a fire or accident happens inside one rail tunnel, passengers don't have to run miles toward the entrance. They can move through the nearest cross passage and enter the protected service tunnel. Maintenance crews use those same connections to reach broken equipment, inspect the tunnel lining, or respond to emergencies. The rail tunnels also connect to each other through giant crossover caverns under the sea. These spaces let trains move from one track to another, so operators can close part of the tunnel without shutting down the entire route. So when engineers talk about connecting an underwater tunnel, they don't only mean joining both ends, they also mean connecting everything sideways. Rail tunnel to service tunnel, one track to another, passenger route to emergency escape route. And that's only part of it, because trains don't just move through a tunnel, they push air through it. Inside a long tunnel, a fast-moving train works like a giant piston. It compresses the air in front of it and drags lower-pressure air behind it. That pressure can slow the train, shake equipment, and make the ride uncomfortable for passengers. So the Channel Tunnel uses piston relief ducts about 2 meters wide. These ducts connect the 2 rail tunnels and give the compressed air somewhere else to go. Fresh air also moves through the service tunnel, and if a train stops underground, extra ventilation systems can pump air directly into the rail tunnels. Then there's heat. Moving trains, electrical equipment, brakes, and friction all release energy inside a space where heat can't easily escape. Engineers estimated that temperatures could climb to around 50 degrees Celsius or 122 degrees Fahrenheit. So they built huge cooling plants on both sides of the channel. Miles of pipes carry chilled water through the tunnel and pull that heat away. And below the tracks, drainage channels collect any water that gets through. Pumps move it toward collection points. Sensors watch for leaks, pressure changes, smoke, heat, and structural movement. Overall, from the surface, an underwater tunnel looks like one simple line connecting two places. But beneath the water, it's one of the most complicated megabuilds humans have ever figured out. And that's how underwater tunnels are actually connected. Now, if you like stories about mega projects, bold architecture, and the engineering behind the world's most extreme infrastructure, make sure to subscribe to the channel and also check out our previous videos about unique engineering and insane mega projects.